I'm going to tell you a little bit about we are going to tell you about the saga of Fuse. This is a three-part presentation. I'll talk first, and then Dennis McCarthy will tell you about how we actually did it, how we got from essentially the beginning of CD to the end to a very successful launch. And then, and this is a lesson, I think, here. The sailing was not smooth after launch. Things worked well for a while, and we knew there were some problems in the wings, and we were worried about them. And of course, the problems you worry about are the ones that don't, well, they happen too, but other things happen. So if there's a moral to my tale, it's going to be that stuff happens. Now, what I'm going to do in the sort of 10 or 15 minutes that I have is I'm going to try to first tell you about the mission, what it is. It's quite different from a planetary mission. It was quite ambitious in the scope of the instrumentation. And then tell you a little bit about the history of the early part of the mission, which, as you can see, went on for 15 years. Then Dennis will tell you about phases C and D, and Jeff will tell you about phase E and the extended mission that follows. This is a picture of the launch in June '99. It's an NASA mission, and basically what it has is a large FUV high-resolution spectrograph, and it complements the Hubble Space Telescope. If you were to equip the Hubble to do this spectral region, it would require enormous investment in technology and provide an awful lot of risk for the Hubble. So the solution, in a way, is you build another satellite, a dedicated, specialized satellite. We are in a low Earth orbit. We operated for about 8 years, and we were very successful in acquiring data of interest to the astronomical community. It is a PI class mission. It became a PI class mission of the type you think of as a PI class mission only really at the end of phase B. And it was operated as a observatory. In the first 3 years, half the time went to the PI team, half the time went to the community. And then after that, in the extended mission, all of the time went to the community. It was very popular. Oversubscription rates were a factor of 3 or more. This is not a little instrument. If you were to look at the instrument, it stands a little shy of 20 feet high. You know, it's 3,000 pounds. It's a big thing. And just shipping it is a big deal. And so I say it's 1.5 mid-X. Maybe when the mid-X has really got small, it was 2 mid-X's. I don't know. But there were no mid-X's at the time that this mission went into CD. And in fact, we were sort of the pipe cleaner for how to do a PI class mission. Now, why should you do this? Well, basically, because of technical reasons, the Hubble cuts off a little below 1,200 angstroms. Unfortunately, the spectroscopic region really extends to 912 angstroms, where the photoionization of hydrogen makes the galaxy opaque. So there's a gap. And Fuse basically covers this gap. And the reason why it covers this gap is that's where the transitions are. You know, you think about your elementary physics, you know, where's the resonance in the atoms? And the answer is it's above 10 volts. And that's where all the strong transitions are. And so Fuse is in this region. And if you want to do things like deuterium, you want to look at very hot plasmas of 300,000 to 1,000,000 degrees, then you've got to work in the spectral region. And it's very, very hard, using the indirect evidence that you get with Hubble, to always know what's going on. We were a very broad mission. We addressed a very large number of problems, ranging from deuterium, which is related to the abundance of baryons in the 3 minutes into the Big Bang. There's a big problem, by the way. One of the problems we have is we have models that predict how many baryons, based on the number of baryons that we know were there, we think we know were there in the beginning, we can predict how many baryons there are in the local universe at z equals 0. Half of them are gone. Where are they? Half are missing. The answer is they're in very hot plasma that's very difficult to observe. Now, Fuse can't observe that plasma either, but using the O6 transition, which kind of can measure slightly cooler plasma, we can sort of see the hair on the dog and therefore decide whether or not there's a dog there. And the answer is there appears to be a dog there. That's where they're hidden. Whoops, let me go back. What did I do? Thank you. Another discovery was that we knew that the galaxy had a corona, but we were quite surprised to learn that beyond the corona, there's a huge halo that goes way out. And it's very hot, it's very thin, and you don't see it very easily. But Fuse could see it because we could see the incoming high velocity clouds, and lo and behold, you could see almost like a shock wave on the front end. And then another question, this is something we didn't think we never thought of it. God was good to us and gave us this problem. I can remember sitting in the room and one of my colleagues said, let's look at an A star. And I said, Alfred, why do you want to look at an A star? That's crazy. They don't have any emissions in the far ultraviolet. We know that. He says, let's look. And so we saw this very strong chromospheric line from the central star, very broad, huge. What's going on? Then you suddenly realize it's the interaction between the disk and the star, which is still not well explained at this time. Well, and on and on and on, okay? All right, so this was a very successful mission. We had lots of programs, lots of observations, lots of data. I would say about 1,000 scientists worked on the program over the 8 years of operation. Very successful in terms of data, many publications. We stopped counting in March of '08. Now, one of the things that you have to remember, the data is in the massed archive at the Space Telescope Science Institute. It's accessible over the web, and among astronomers, archival research is a flourishing field. I'll give you an example. On the Hubble Space Telescope, half of the papers that are published that refer to the Hubble Space Telescope are on new data. The other half are on archival data. Right? There's a lesson there, I think, for the planetary community. And I say this as a person who's involved in Voyager, and my colleagues have tried to dig back in the Voyager data. It's very hard. If you're in the PI, if you're on the team and you have access to all the software tools, it's fine. But if you're an outsider, you're dead. And that's not true in astronomy and astrophysics. And the data sets are generally available to any astronomer, and they are used. The other interesting thing that came out of this mission is that the cosmic origin spectrograph on the Hubble Space Telescope is directly based on the technology that was developed in this mission. And a lot of the learning pains that we went through with the detector and with the gratings were transferred and were an enormous saving in the construction of this instrument. Okay, now I'm going to change gears here, and I'm going to tell you a little bit of the saga. At the end of the Copernicus mission, a group of scientists, one of them was Ed Weiler. Ed actually worked on the Copernicus mission. And so he and a couple of his colleagues were just talking about the fact that it would be wonderful to have another follow-on mission. And in fact, the field report, the CADL report that at 80, recommended it as its highest priority for small to moderate sized missions, a far ultraviolet spectrograph. A working group was set up. We wrote a report, and we baselined a grazing incidence telescope, not as something as challenging as Chandra, but we wanted to, in order to get the short wavelengths, we wanted a grazing incidence. Delta class missions in those days were much more, shall we say, ambitious than explorers are today. Now, the original edition of this slide did not say extensive discussions. It said talk, talk, talk. Who was going to join in the party? You never have enough money. So who's going to join in the party? We talked to ESA. We talked to the various national entities. And we talked to Australia. We talked to the United Kingdom. There were many different players. And eventually, it did look like ESA was going to play. We put in an Explorer in 1986, which unfortunately followed the Challenger accident, and there was a delay going into Phase A. When I finished getting that proposal in, the scramble to get the proposal in, and I took my wife Doris out for dinner. She loves Chinese food, so we went to a Chinese restaurant that we like. And of course, at the end of the dinner, there's always a fortune cookie. So I open up the fortune cookie, and it says, "Beware of what you desire. You may get it." And I think that's probably a moral to the story. In any case, we originally baselined an ELV, a dedicated spacecraft, and ESA was going to be part of that. We were going to be in high Earth orbit. It was really a very ambitious mission. Unfortunately, in 1988, the ESA bailed out. Okay, they decided they wanted to build the Huygens spacecraft on Cassini, and they couldn't do both. Well, at that point, the only way out was the low Earth orbit Explorer platform, and basically a shuttle mission would take a previous mission off the Explorer platform and put us on it. I wasn't happy about that because nobody wants to get hooked up to the shuttle, but that was the only way to survive. We did, in fact, enter Phase B in '89, and as I mentioned, we had now had to go to low Earth orbit, and there was a big concern in the community because of the cost of Hubble. It was clear that low Earth orbit could be very complex and very expensive. All right, they said you're going to need another institute. You're going to have 2 institutes on San Martin Drive. So more to come. Okay, more to come. We thought we were going into Phase B. All right. Now, I have to say that by this point, I want to make a point that we had gone through a couple of what you would call D-scopes. We had gone from grazing incidence to normal incidence, and there was a case where the technology came to the point that, in fact, it was attractive to go to normal incidence. So it wasn't really a D-scope. In fact, I think we certainly reduced our risk, and we probably kept the same performance or better. We also went to what's known as a delay line type detector, which allowed us to get very, very many pixels at the risk of drift. In other words, it wasn't geometrically as stable, and we paid for that. On the other hand, if I had kept my first choice in detectors, I think I would have never gotten it. All right. I mean, the history of that other detector was that I don't know, $20 million for a very small one on STIS, and we had a very, very large one on Fuse. It just never would have happened. But the problem was, having solved those problems, circumstances caught up to us. If you remember, this is the era of faster, better, cheaper, or that's when it was going to happen. And as the pressure was put on the Explorer program to do something, it was clear that the large Delta-class Explorer missions, and in particular Fuse, was clogging the way. So the solution was, a phone call. And a phone call came the day after Labor Day. Labor Day, I always am very relaxed at the end of that nice long weekend. And I was chair of the department at that time, so I got a call. I was up in my department office. And I was told to meet Ed Weiler and Weidman. And about 20 minutes, I ran downstairs and I grabbed Dennis. We went to my office, and this is the call we got. Okay, it was canceled. Now, NASA really wanted to preserve the science. I mean, I wasn't like, they say, oh, all right, cross this off the list, we're moving on. I think people were pretty upset. But they were really caught in a bind with the budget crunch. And then began a very intense week. I can't tell you all the people we saw, okay? I'm not allowed to. But the point is that the science community, in the person of people like John Bacall, played important roles. We talked to all the players, and I must say one of the important things in our case, remember, the astrophysical community is kind of wired. There's a lot of herd things that go on. And there were people who wanted to start email campaigns. They said, well, I can get access to the American Astronomical Society email list. And I said, no, please don't. So there was an issue of keeping the community damped down. Finally, and if you can believe this, come on, here we are. 4 days later, Friday afternoon, Dennis, Mark Perry, and myself met with Wes Huntress, and basically this is the outcome. We created a PI class mission. Okay, so that in fact was the first real PI class mission in the Explorer line. PIs had always been PIs of the instruments, but they never took complete control of the mission. And we were given just about 4 months to prepare a CD proposal. And of course we had something very ambitious. We had a high Earth orbit, on and on and on. And we had to restructure that mission. And you talk about the interaction between scientists and engineers being important. I can tell you it was very important, okay? It's very important. When you decide on your orbit in 1 day, you got to have all the players in the room. It's the ultimate skunk works, okay? And Fuse, by the way, was not, we were distributed in many ways, but the core group was in Baltimore at Hopkins in one building. And I mentioned I also remember I talked about a higher Earth orbit versus low Earth orbit, and in the end we were to show, with a lot of help from the Space Telescope Science Institute, that if you had a simple instrument without a lot of modes, you could also build an operation system that was relatively simple. Not cheap, just simpler. Okay, so Phase D began in November, day after Thanksgiving in '95. The story that Dennis will tell then is how we got from there to June 24th, 1999, when we launched. Thank you.
So I went to this Chinese restaurant. I mean, I think let's see here. after the Kobe mission, which we talked about yesterday, I was the deputy for the Hubble repair mission, the first repair mission. And after that, that was it. It's time to go. So I went to Hopkins. I was going to learn to be a teacher and build an instrument. And I was there for 6 weeks to the day when Warren and I got this phone call from Ed Weiler. And I'm looking out the window and I went, I don't have tenure. Warren's got tenure. I don't have tenure. So we went to, as Warren said, we can't tell you all the places we went because we just did what we had to do. And I can tell you that Ed Weiler, since I knew him and know him, at the end of this telephone call, he said, Dennis, do what you got to do. And on the way home, I went, I know who to call. So we made some phone calls and we went to Washington and met some people. And it turned out that if you have full cost accounting, Fuse was going to be done in-house at Goddard, which is another training program like Kobe, which was good. But with full cost accounting, it was over $300 million. And the system had decided faster, better, and cheaper, and $300 million wouldn't do it. So we went downtown and we met some people, and they said, you know, if you could do this for a third of the price, we'd consider it. And I said, I'll be back. I had to leave to make it look like we gave it some thought. But since I didn't have tenure, the answer was going to be, we'll do it for a third of the price. And in the end, the bottom line was we did it for $120 million versus $300 million. And there were a lot of questions like, how can you possibly do this for 1/3 the cost? Well, first of all, we made it a PI mission. We concentrated the work at Hopkins. And I can tell you, and I'll speak to this, system engineering played a big role in this. And the other thing is we procured what was available commercially. We bought a spacecraft that was fixed price. We developed a ground system that was fixed price. And as I said yesterday, if you can fix 2 of the 3 things of the triangle, if you can fix the ground station and the spacecraft, then you can develop the instrument. And that's what we did. Well, I got it. So if you look at this, Warren alluded to the fact that this program has 3 countries involved, the United States, Canada, and France. It has 4 universities, Hopkins, Colorado, and Berkeley, and then we had the University of Puerto Rico, which is where the ground station went. We ended up with a commercial spacecraft from Orbital Sciences, and we ended up with on a fixed price contract, and we ended up with the ground system, which was a fixed price contract from Allied Signal, and they also developed the Operations Control Center, which actually ended up in Hopkins in the Bloomberg building. So if you look at this complex organization and you're going to do it for 1/3 the price, you're going to have to do it differently. And I'm going to skip the next chart because you've already heard some of this yesterday, and it's a lot of motherhood, but I think I'll speak to this by the time we get done. So to do it for $120 million, we designed it to cost. And as I said yesterday, I put a little logo in my office, which was right next to Warren's office. And it had one word in it that said the word was changes, with a circle and with an X through the word. We're not changing anything. And I think Warren speaks to it, and there's a chart further back. It probably took a year for everybody to understand we're not going to change it. I mean, we've got to get this done on time. We did it in less than 4 years, and we're not going to make any changes. And because of the fact that the spacecraft was a fixed price contract, you could not change anything at the interface between the spacecraft and the instrument. The other thing was the ground system was a fixed price contract. And between the spacecraft and the ground system, you can't change that either. It actually made it easier for me, once Warren understood what I meant. I was going to tell you something, but we also tailored the documentation. I think what I found, and I know what Jim Fanson believes about 7120, it was not there at the time. We developed a lot of processes, and we eliminated a lot of documentation. And I can tell you what we did when it came to procedures. Normally, when on other programs, the procedure's written, and then there's another document that explains why we're going to have to do this, and there's a plan, and then there's a procedure. What we did is we put the plan as page 1 of the procedure. If we can do it in 1 page, that eliminated a whole set of documents. We also streamlined the decision and the approval process, and we actually did it online. All of the change orders and all of the documents were electronically in the system, and people could put changes into the system, and then we did it all electronically, which made a big difference. The other thing, and I'll show you a chart, the key to this whole thing in my mind, and it's the key to most programs, is systems engineering. You could not do this program with people all over the country and in other countries if you did not have a good system engineering team, and that to me was the key to this program. We integrated the team. I mean, in the end, Warren and I sat next to each other, and the scientists and the engineers, it was not a skunk works, but they were all at the Homewood campus in Baltimore, and they all worked together. And I think Warren, since this program, since I left, it's become obvious it took months for us, for the engineers and the scientists, to understand what they were saying to each other. It would be a lot of this wavelength and this and this. And after a while, and it was just a process, the engineers and the scientists got to understand what each other meant. This program became a PI mission. The PI, Warren, was responsible for this program, and everyone understood he was responsible. I, as the project manager, managed the cost and the schedule and the technical. But as far as the reserves, as far as the schedule, and as far as the cost, the PI was responsible for that. I think the key was the system engineering. As I said, we had, as you pointed out, we were not responsible for the launch vehicle, but we were responsible for the interfaces to the Delta launch vehicle. We had a system engineer that worked directly with that launch vehicle. We had a system engineer directly responsible for the ground system, a system engineer for the spacecraft, and of course various instruments systems engineers. And we had one mission systems engineer. And this, to me, was the key for us to pull this entire complex organization together. I think the key is systems engineering. We, as I mentioned, we had a web-based tool because there were people throughout the country, at Berkeley, at Colorado, at APL, at Hopkins, and in Canada. And I think because of the fact we could do all of the processes and procedures electronically, it made a big difference, and it was very efficient. The engineering change orders on CCBs, Configuration Control Board, we did that electronically, and people did not have to come to Baltimore. They could do it and send their comments in, whether they approved the change or didn't approve the change, and it was all done electronically, and you can do it with people spread out if you do it that way. I'm not going to read this chart to you, but there'll be a quiz when I get done. I think the key to this program, there was a lot of keys to the program, but one of the keys was that this spacecraft was fully redundant. And the other thing was, it was a fixed price contract, and all of the fee for that contract was based on on-orbit performance. It was not based on the delivery of the spacecraft. It was based on the performance of the spacecraft on orbit that was evaluated every 6 months. And because of that, you can rest assured, this was Orbital Sciences, that spacecraft was fully tested. Because if they wanted their fee, the spacecraft had to work. And I think the other thing was, because it was redundant, it gave us the ability to know that we did not have that many single point failures. D-scopes. I mean, Warren mentioned the fact that before I got there, they were de-scoping and changing the design of the instrument. When we got involved with this program and when we restructured the program and said we'd do it for a third of the price, we actually went off on a retreat, which now is called an advance, I think. And I think this is important. We took everybody on this team to a hotel like this, and we spent 2 days, and it was done before it had to be, before it was needed. And if you do it before it's needed, people will tell you what they could do, figuring they're not going to have to do this. But you try to, after a while, you have this group environment, and everybody tries to come up with something they could de-scope. So we ended up with 2.5 pages of D-scopes. Well, we could skip that test. We could skip this spare. We could not do this analysis. And it went on and on and on. And I think the key was to have it done before it's needed. Because when it's needed, you bring them all back in the room and everyone's going to go, well, it can't be me. I can't de-scope. So we had the list. And I can tell you, as we went through the program, most of those D-scopes came to fruition. But I think you need to have it in advance. And the other thing was, this program had a minimum performance floor, which is now a requirement. And because of the fact that we went off and discussed the D-scopes took us down to the minimum performance floor, if required. I think the other thing we did was we formed our own review team. We brought in people that, and I think you saw yesterday on Kobe that we brought 3 senior engineers in to evaluate Kobe. We did the same thing on Fuse. We didn't get caught up in the normal, without being derogatory, the normal system of reviews. We brought in senior people who were retired, who reviewed this program periodically before we would have a review with the government. And these people were so helpful, and it worked very well. The other thing is we had peer reviews. And we had these over and over and over again through the life cycle of this project. And the peer reviews were not view graphs. They were detailed reviews. We brought in a senior electrical engineer or senior mechanical engineer, and we would go through the drawings and go through the schematics. And those were the peer reviews, and I think that was the most helpful thing we did. The other thing is this review team, the review team that Warren and I put together, it worked out real well. They would actually present to the NASA review team what their findings were. But they were done, it was done independently, but it also worked well. I think, as Warren pointed out, I think this was the first PI mission. It was a big satellite, and it was $120 million. I think the key was to procure the spacecraft off the shelf and procure the ground system. We actually put the ground system at the University of Puerto Rico, and it was an autonomous ground system where Hopkins and Homewood would send the ephemeris data to the ground station, the antenna down at Puerto Rico, and it would acquire the satellite, and it was done autonomously. And I think this is the key to all your programs. Buy 2 and develop 1. And I think this was in 1996 that we bought that spacecraft, fully redundant, for $35 million. That included the on-orbit performance fee. The ground system was fixed price. The international partnerships, I think Jeff Crook's going to talk about that. That was difficult, and we were in, by the time I got there to do this in less than 4 years, that became a hard thing to do. I mean, ITAR was not as formal as it is now, but it was difficult to deal with. And I think Jeff's going to talk to them. I think that the science team, because they worked directly with the engineering team, after a while they realized we're not going to change it. I mean, this was academia where I worked at Hopkins. We could sit there and study it and analyze it and write a report. No, we're not doing that. I mean, they wouldn't come to my office because the answer was no. I think the key was the interaction between the scientists and the engineers. It took months for us to understand each other, but that to me was the key. And it was $120 million versus $300 million. So we accelerated the program by 2 years. We reduced the cost by 60%. The Fuse instrument basically remained the same as what it would have been with the Goddard larger program. There are credible spacecrafts that you can buy and ground systems you can buy on fixed price contracts, which allows you to develop the instrument and control the cost. And I think the key to this program was the fact that it had an adequate Phase B program. So when we got there to do Phase CD, the Phase B design was intact. And I think the other key was that we were emphatic that this PI was responsible and it was his program, and we worked directly for the PI. As Warren would tell me once a year, I serve at his pleasure. Because I don't have tenure. Are there any questions?
Thank you very much.
I should clarify, I only took over the mission systems engineering a few weeks before launch, so everything they were talking about was actually Larry Frank's doing, and after that it was up to me. I'm going to be talking a lot about Phase E today, and I think I'm the first one who's really saying much about that. Some of the lessons learned really are peculiar to our circumstance. You're unlikely. Anyway, I'm going to try to, in each case, at least distill lessons that I hope will be useful to you. This is the sort of dramatic points in our on-orbit timeline. All the items in pink here have to do with gyro failures. All the items in purple are reaction wheel failures. And the green are positive events where we've uploaded new flight software to deal with those problems. One interesting point is that we first got our on-orbit indication of problems with the ring laser gyros only 6 months after launch. As Dennis mentioned, the gyros had been reworked sort of in the middle of our thermal vacuum testing. The vendor thought they had solved the problem, and so we went into launch thinking that those were not an issue. And I'll also indicate that the reaction wheel problems we had no hints of prior to our in-orbit problem with them. And then finally, as Warren mentioned, we decommissioned the satellite in October of 2007. Warren and Dennis have already mentioned this briefly. We did all of the mission operations and science operations and community support from Hopkins. I'm not sure for most of the planetary missions if you'll ever have all those functions under one roof, but in some ways it was a very nice circumstance, because it really made it a lot easier to deal with the on-orbit problems when everyone was physically co-located. Warren made the point that the operations were simple compared to other low Earth orbit missions, but in a lot of respects, when I look at the other proposals I've been involved with for explorers, our operations were more complex than any of them. It was very much like Hubble, apart from the fact we have only one instrument, and in fact we leveraged a lot of our planning software and our data processing software from the Space Telescope Science Institute. We were sort of the first mission where they exported a lot of those tools to other missions, and so we benefited a lot from their efforts. So I'm going to start by talking about a lot of the problems we encountered in the first 6 months of the mission. A lot of them were not very major problems on the grand scheme of things, but a lot of them do illustrate what can go wrong when you don't think of absolutely everything you might need to test during INT. So the first example I'm going to give here is the fact that our 4 co-aligned telescopes didn't stay co-aligned once in orbit. We found that whenever we would reorient the spacecraft to a significantly different angle with respect to the sun, that the 4 channels would all move by, say, 10 arc seconds. When you have a 1 arc second slit, that's much too big. The lesson here really is that even though we had a very extensive thermal vacuum testing program, this was not something we could test in the thermal vac tank. There was no way to simulate moving the sun around inside the thermal vacuum chamber. I don't know if any of you will have that particular problem, but the point is you really need to always be thinking about what it is you can't test and what it is you should be starting to worry about as a result. We worked around this primarily by just changes to our on-orbit procedures. It did add somewhat to our overall workload in Phase E. So the real lesson here is just simply if you can keep your operations flexible, it may stand you in good stead. Another problem that shouldn't have happened was that the embedded processor in our detectors was susceptible to single event upsets. They were apparently quite well rated in terms of total dose, but down in the very center of the SAA when we would go through, perhaps it was a multiple event thing that would cause the SCUs, but then the processor would have to be rebooted. This was in itself not necessarily that big a problem, but during integration and test we discovered that the high voltage supplies in the detector had a potential failure mode that the software wasn't watching for. So we had to update the software in the detector, which again would not have been a problem except that the detector stored all the code in proms as opposed to double EEPROMs. So we would have to reload the software from the ground every time we had an SCU. And because you had only a few 10-minute contacts a day, that was a very painful process. And then you have to ramp the high voltage back up. So once a week, we were losing 1 to 2 days of observing time, which was not acceptable. And so the way we dealt with that is that we had plenty of spare double EEPROM in the instrument processor, and we had the ability to reprogram the instrument processor. We had all the flight software developers still available. So we stored the detector code in the instrument computer and added commands to the instrument computer to reload, to detect SCUs and to reload the code autonomously. It was a few lines of flight software, but you had to be able to update it, and a couple of if statements and scripts that were watching telemetry. But again, the point was we actually had real margins that we had carried into launch. If you find yourself in Phase A or B mentally starting to use up some of your margin, you should stop and take stock about what you're doing. This is another subtle problem. The bulk memory manager in our instrument computer had a minor bug. When we would finish an observation script and delete it, there'd be one little couple of bytes of the header that wouldn't get deleted, and it would fragment the memory. Now you would think, well, this is a stupid problem. But it was only evident after you had done a couple of weeks of continuous operation. Well, there was never any test we ever did on the ground that ran the code uninterrupted for weeks at a time. All the development testing, you would always want to make sure you had a nice, clean, well-defined configuration. So every day you come in, you reboot everything, power it up, start clean. So this problem would never manifest itself. And then once you get to mission sequence testing with the real satellite, again, test time in INT is very expensive. You've got lots of people clamoring to do different things with the satellite. You're never going to just take 2 weeks of time out of the schedule and run a mission sequence test. Just simply wasn't a practical thing to do. So again, this was a couple line update to the software once we detected it. So it was not a major problem, but the real lesson here is simply that there are some things that you're not even going to think to test, and it can come back to bite you. Another very subtle problem came out with a processor in the fine error sensor. There was a very subtle bug here that where one interrupt would get clobbered under very unusual timing circumstances. It was a sort of one in a million type logic race condition. But that timing would depend on just where the guide stars happened to be in the field of view. So during INT, we would maybe have a dozen different test configurations for the fine error sensor we would execute. We thought those were stress conditions, but it wasn't really a stress issue. The processor was not being overloaded. It was just a random event of when certain events that were tied to the bus schedule collided with things that were driven by the CCD macro timing. So it was a kind of bug that you would have to run a million different cases in INT. But here's an example where this particular process was running maybe a dozen times a second. Doesn't take very many days running a couple dozen times a second to hit your 1 in a million chance. So this is a example where to really run a test like this, you need to have almost a Monte Carlo for your test conditions and commanding of your system. I can't even guarantee you would catch it then, but it was the kind of thing that just want to put a bug in the back of your minds. It's not always easy to determine what your worst case conditions are to run your tests on. There are lots of other minor problems. None of them would be worthy of note, the kind of thing that anyone's going to run into. But the workload just turned out to be underestimated by, say, about 10%. And it's probably impossible for anyone to really predict what their workload is going to be at the 10% level far in advance. So we wound up, I forget, it was just a couple months into operations, we decided to hire 2 more people. And suddenly everyone was able to get some sleep. And the other issue there is you can't predict where your problems really are going to be. So just cross-training of your staff is invaluable, and that way you can actually shift resources as you need them. Preparation for the extended mission was nothing really remarkable, but it was a very large effort. The ground station was autonomous, but all the procedures in the control center were not, and it was quite a bit of work to automate all of that. I'm not sure if nowadays a lot of the commercial ground station providers or ground system providers and mission ops centers probably already have a lot of this stuff automated, and maybe that won't be such a big deal. But if that's not the case, it's important to actually plan a fair bit of resources to managing that effort. Okay, gyro failures. We did get some sign of this during INT. The vendor thought they had identified the problem. I've heard probably about 2 years ago that they think this time they really have identified the problem. The difficulty is the gyros even so lasted several years. If you identify a problem during INT, your vendor claims they've fixed it, there's no way you can then sit back and run 2 years or 3 years or 5 years of life testing. So you're going to have to decide your own inherent appetite for that kind of risk. In our case, we really didn't have a choice. At that point, we were a couple months from launch. There was no way we were going to go and buy completely different gyros, qualify them, modify all of our systems to use them. Once we faced up to the fact we were going to have to live without gyros, we did have a extensive skunk works program. Actually, extensive, not the right word. It was really only a handful of us doing it. The thing I want to talk about briefly is that once you're in that kind of situation, the performance is nowhere near as predictable as it is for a normal flight program. In a flight program, you're designing your attitude control system or whatever it is to be in a linear regime. You've got lots of margin. You can define what the margin is. You can define stress cases, and you can then run tests to verify that you can handle the stress cases. In a situation like this, you can't really define what the stress cases are. You start propagating noise. Once we had lost reaction wheels, you start getting positive feedback between lack of controllability and lack of being able to propagate your equations of motion. So you just simply have to live with not necessarily being able to predict that your system is going to work. When the alternative is just turning off the mission, it's not a difficult choice to make, but it gets there. The point here is simply that there are times you can't necessarily define what your stress cases are or figure out how to test them. The reaction wheel problems were quite a bit different from the gyros in the sense that we really had no clue prior to launch. When Orbital was deciding which reaction wheels to pick, they really had no reason to pick one vendor over the other. The main reason they went with the wheels we did was that they had greater resolution of the wheel speed brought back in telemetry, and they thought that would be useful. It did turn out to be useful for dealing with the gyro problems. We had a much better way of measuring exactly what torque had been applied, but it was really a very much second-order decision prior to launch. Once again, there's a lot of rework of the flight software involved. One reason I'm bringing this up is that since our problems, quite a few other missions have had problems with their reaction wheels, and I've been called in on a number of CDR panels and providing other advice. And one of the things that people don't tend to think about is that they focus entirely on the ACS flight software. And in the case of dealing with the reaction wheels, the changes to the flight software were pretty minor. I mean, the changes for dealing with the gyros were major, but dealing with the reaction wheels, the changes to the flight software were small, but the changes to the ground system were enormous. It was an order of magnitude more increase in complexity in our observation planning. And so my word of advice for anyone who's ever faced with this situation of having to do additional redesign work is to think about your ground system. The impacts there can be a lot greater than on the flight system. Okay, some of these lessons learned are not necessarily tied. I didn't want to give all the examples, but I'm going to talk to a few of these in more detail. You can't make your optical end-to-end tests high enough fidelity. You can't do them early enough, really. You probably will not be able to do them really as well as you would like. They're expensive. And then finally, as they say in the commercials, they are priceless. We put a lot of effort into our optical end-to-end tests. They were extremely valuable. We found one problem right in the middle of many months of thermal vac that was a very good thing indeed that we found. And we were able to rework some of the hardware and go back into thermal vac and verify we'd fixed it. But the lesson here is that you really have to have funded schedule reserve all the way up to launch. You can defer a lot of tests into your observatory level testing. Some of them don't make sense to do before observatory level testing. But if you find a problem, you'd better have time and money to fix it. You look at an Explorer program or some of these other programs, your total development schedule is 3 years. You barely fit anything in to those 3 years. And then you also have to have time to fix things that you find. It's very easy to write a success-oriented schedule, and it's another to actually have to live with it. Another sort of motherhood and apple pie statement that a lot of vendors will give lip service to is you design your instruments always with an eye towards facilitating verification. Don't give it lip service. I mean, it's probably the most important thing you can do in designing your instruments is trying to figure out from day one how you're actually going to verify that it works. We put a lot of effort into that. Every single requirement that we flowed down from our science requirements down to our lower level requirements, we had tests for. And we verified every one of those. There were a few things we didn't think to write a lower level requirement on. They weren't necessarily crucial to our prime science, They would have proved useful to some of the other science we did. They weren't part of the flow down. We didn't do analysis on them. We didn't test for them. And a few of the things just simply didn't work as well as we would have liked. So I don't want to go into all the details. Some of them are much too specific to our Fuse instrument, but it's just a sort of a warning that you can't really think of everything no matter how hard you try. But if you don't try, you really won't get it. A high-fidelity flight ops test bed was not something we had prior to launch. We had it after launch when we assembled the different software development test beds from the spacecraft and the instrument. This is a lesson learned that really only struck me as I was putting together these slides. We did all of our control center procedure development, or tested them anyway with the real satellite. During INT, it was always a struggle. The control center would want to do a test. The people on the ground were doing something with the satellite. We were always fighting over some schedule, when to put a test in. I really like to do this test next Tuesday, and the guys at the Cape would say, well, we've got something else going on that's going to take 3 days. How about next Wednesday? And then you say you want 2 days, and they'd say, no, you can only have 1 day. So every major procedure that we had to do, we did get tested. But the example of wanting to run a mission sequence test for 2 weeks straight was something we simply could not fit into the INT schedule. And there was no really obvious, compelling reason why we had to do it. But if we'd had a test bed, it was the kind of thing where the people on the ground could have shaken out all the procedures for how are we actually going to string together weeks or a month of observations, how are we going to generate the command loads, how are we going to actually do this on an ongoing basis, and we'll actually see what the workload is. That's the kind of thing you could have done if we'd had a test bed. When I've tried to make this argument in some subsequent proposal efforts, people would say, well, that's an enormously expensive thing to do. But when I've been thinking about it, I don't think that's really the case. Every piece in this kind of test bed is something you're already developing for your instrument software developers, your spacecraft software developers, or whatever. And if you just decide on day one you're going to have this, you'll find, I think, that it's not so expensive. The hardware is typically just PCs. For the case of the flight processors, you really want a representative piece of hardware, but it doesn't have to be space graded. It can be commercial grade parts. I think it's something you really ought to give serious consideration to. The sustaining engineering contracts, I think, are self-evident in our case. We had support from all the component providers, and including from the Canadian Space Agency. When we started having problems with the gyros, we needed to rework the fine error sensor software, and so they stepped up and basically provided that support for us and redesigned the FES software. For a planetary mission, this bullet here on TDRS is probably not so important. During our in-orbit checkout, TDRS scheduling was very painful. We didn't use it very much then. Later in the mission, they had developed some really wonderful tools for being able to access unscheduled TDRS time. That was essential for surviving some of our days with dealing with reaction wheel problems. One thing I haven't talked about till now, but I thought I would just mention it. Fuse had very stringent contamination control requirements, more stringent than Hubble. And a lot of effort went in from day one to figuring out how we were going to manage that. And I just want to say here, I don't know how many of you will be interested in this, but you really can do it at modest cost if you figure out from day one what you need to do. Dennis mentioned that I might talk about the fine error sensor development with the Canadians. The lesson learned there, I think, if you've got international partners, is to, again, from day one in your MOU or whatever, establish the mechanism by which the project is going to control what goes on in the international partners, industrial partners. With Fuse, the industrial partner in Canada was ComDev, their contract was with the Canadian Space Agency, not with us. So whenever I wanted to relax a requirement, I couldn't just tell them, I couldn't just write a little letter and say you can relax this. I had to go to the Canadian Space Agency and have them tell ComDev to relax this. It was a much more cumbersome procedure than one would have liked. I don't know how to do this and provide advice in a very general way, but to think about this issue when you have international partners and try to establish from day one what the actual mechanism is for making sure that ICDs are, have legal force across national boundaries, how to decide, how to establish which requirements documents have legal force across international boundaries. If it all is done through the contract with the foreign partner, it can make life very difficult. And there was one other bullet I was going to add, but it escapes me at the moment, so I'll just stop here. Thank you.